Hi friends, today we are going to discuss sinusoidal waves in relation with electromagnetic waves. Also we are going to represent this sinusoidal wave in complex notation. Okay. First of all, why we are studying sinusoidal waves in relation with electromagnetic waves? Generally, most of the generators of electromagnetic waves produce waves which are varying sinusoidally with time. Hence, we are studying some properties of some representations and notations of sinusoidal waves. Generally, a sinusoidal wave can be represented as f of x comma t is equal to a cos k into x minus vt plus delta. Here f of xt represents the displacement at any instant of time due to the wave propagation. Displacement at any instant of time due to wave propagation. And capital A, which is known as the amplitude of the wave. We already know what is meant by amplitude. Amplitude is the maximum displacement from the equilibrium position. Then that is A, and cos of k into x minus vt plus delta. That argument of cosine is generally known as phase. Argument of cosine is generally known as phase. Here k is wave number, x is the position, v is the velocity with which the wave propagates, and delta is the initial phase or phase constant. In certain books it is known as initial phase, and some others are referred as phase constant. Okay. Now look at the figure, which is showing a wave propagating in x direction. Now we are considering some initial conditions. Initial condition means at time t is equal to 0. We are assuming that our position is at origin. We can fix origin anywhere here. I show that origin as here, placed as here, where f of x0 line meets with x axis. Okay. So here I am considering my origin. And as from this figure, and as from our equation 10, when we are putting our initial condition at t is equal to 0, x is equal to 0. X is equal to 0 means we are considering the point at origin. When we substitute these terms and x is equal to 0 and t is equal to 0, we will get f of 0 comma 0, x is equal to 0 and t is equal to 0. Hence we can write f of 0 0, that is equal to a cos delta. That means the displacement is not maximum at x is equal to 0 initially. The presence of the term cos delta, or the presence of the term delta or initial phase, makes this happen. If delta equal to 0, initially we are assuming t equal to 0, x is equal to 0, and delta is again equal to 0, then we will get that f of 0 0 is equal to a cos 0. The value of cos 0 is 1, that is its maximum value. Hence we can say that the amplitude is at origin. Maximum displacement is taking at origin, or central maximum is taking place at origin. This is true only if the initial phase is 0. If it is not equal to 0, this maximum, where will this displacement will become maximum? That can be found if the argument of cosine function goes to 0, because cos 0 will give its maximum value. That means k into x minus vt plus delta, or I am rearranging this equation as here a cos k, k is taken outside this bracket, so this will be like this, a cos k into x minus vt plus delta by k, or a cos k into x minus of, from this we are taking minus commonly outside from these two terms, then x minus of vt minus delta by k. Here we are putting, not to obtain the central maximum, we have to put this argument equal to 0. K is wave number which is equal to, which is depending upon wavelength, and that will not be 0. Hence, the maximum displacement from equilibrium can be obtained only when this term inside the bracket becomes 0. Hence, when this is equal to 0, you can say find that x is equal to Vt minus delta by k, and we are assuming initially t is equal to 0, then we can find that x is equal to minus delta by k. That is, due to the presence of the phase term, we can find that the maximum displacement or central maximum is not at origin. It is slightly displaced, it is slightly behind the origin at a distance minus delta by k. Since t is equal to 0, x is equal to minus delta by k, where the central maximum occurs. Like this, look at this figure. So this t is equal to 0, but the maximum is not at the origin, it is slightly behind the origin at a distance delta by k, and is drawn like this. Okay. So this shows that the displacement maximum is delayed by a factor delta by k at the origin. The displacement maximum is delayed by a factor delta by k at the origin. This is due to, since delta is not equal to 0. Okay. Now, the some other terms that we have found in that equation for sinusoidal wave, we have mentioned about a amplitude, which is the maximum displacement from equilibrium position, and delta is known as initial phase or phase constant, and the value of phase constant delta is always lying between 0 to 2 pi. Actually 0 less than or equal to delta less than 2 pi, since 2 pi is the repetition of 0, so delta will be lying between 0 and 2 pi. And another term within the bracket that we have found is k. K is known as wave number, which is equal to 2 pi by lambda. Wave number is depending upon the wavelength of the wave, and it is equal to, it is given by 2 pi by lambda. Now, what is frequency? It is when the wave proceeds through the medium with a velocity v, then at any point x, it will vibrate up and down. That means when a wave propagates, suppose this is the point here, x is here, suppose x is here, when wave propagates, this point will move up and reaches its maximum displacement from origin, so from equilibrium position, and return back to this equilibrium position and move downwards and reaches maximum in downward direction, then return back to this point. When we start from here and move here, back, then here, this is one cycle. The time required to complete this one cycle is known as time period. This time period is given by wavelength by velocity, wavelength of the wave by velocity, and that is equal to wavelength. From this equation number 15, you can find that lambda is equal to 2 pi by k, and 2 pi by kv will be the time period. The frequency nu is equal to 1 by t, that is inverse of time period is known as frequency, that is number of vibrations per second is known as frequency, and that is equal to kv by 2 pi, inverse of this kv by 2 pi, or you can inversely write this v by lambda. So these are relations for frequency, time period. And in case of a wave propagation, more commonly using notation for frequency is angular frequency rather than the linear frequency, ordinary frequency. So that angular frequency is given by 2 pi times linear frequency nu, 2 pi nu, omega is equal to 2 pi nu, and we found that nu is equal to kV by 2 pi. So you can cancel this 2 pi with each other, then omega is equal to 8 kV. Okay, now we are going back to our equation number 10, that is a cos k into x minus pt plus delta, and we are taking k inside the bracket so that a cos kx minus kvt plus delta will be the result. Here we can replace kv from 16c, kv is equal to omega, and that is equal to omega, then f of x t is equal to a cos kx minus omega t plus delta, which represents a sinusoidal wave propagating in positive x direction with angular frequency omega and wave number k. Then this is a wave propagating in positive x direction. Similarly, we can find a wave propagating in negative x direction. This is nothing but take just a negative for this expression. Just put a negative sign here. Then a cos minus kx minus kvt, or like this, kvt plus delta, and take minus commonly outside, then kx minus kv is again replaced by omega, and minus is taken commonly outside, hence it is replaced with plus, and plus is replaced by minus. This is for writing, we know cos minus theta is equal to cos theta, hence this cos minus kx plus omega t minus delta is equal to cos kx plus omega t minus delta. So you can remove this negative sign. So f of x t is equal to a cos kx plus omega t minus delta. This is the expression for wave propagating in negative x direction. So these are the expression for sinusoidal waves that is propagating in positive x direction and negative x direction with angular frequency omega. Now these representations involves trigonometric functions such as cos or sine. So it is much more difficult to deal with this cosine or trigonometric functions because it's differentiation integrations, and we cannot separate the space and time parts. So it is much more easier if we replace this trigonometric functions with exponential functions. That is, we are by using the Euler's formula, we can represent this trigonometric function of propagating wave in terms of exponential functions. So that is generally referred as complex notation, or it is also known as phasor notation of sinusoidal wave. And we know the Euler's formula, that is separating real and imaginary parts. If e raised to I theta is the exponential, where e is the exponential representation, e raised to I theta is equal to cos theta plus I sin theta. Here cos theta represents the real part and sin theta represents the imaginary part of the expression. So from our equation number 17 or 18, you can consider 17 if we are considering positive x, and 18 if we are moving in negative x direction. Here I am considering positive a wave propagating in positive x direction. Here we require the cosine term only. Here there is no term like sine here. So from this equation number 19, similar to that equation number 19, we can write a e raised to I kx minus omega t plus delta as a into e raised to I theta is equal to cos theta plus I sin theta, like that, a into cos kx minus omega t plus delta plus I, a is common here, a into I sin kx minus omega t plus delta. Here I represents imaginary representation. So in order to represent a wave propagating in positive x direction, we require only this part, because we are requiring only the real part of expression. So this equation is written as a real part of wave propagating in positive acceleration can be written as a real part of a into e raised to I kx minus omega t plus delta. So this is the complex notation for a wave propagating in x direction. Here some more rearrangements are doing here. Look at this expression, a e raised to I kx minus omega t plus delta. We know e raised to a plus b, e raised to a plus b is equal to e raised to a into e raised to b. So using that relation, here I am writing this as f of x is equal to real part of a into e raised to I kx minus omega t. This kx minus omega t is something b and I delta is something a. E raised to a e raised to I delta into e raised to I kx minus omega t. Okay. Now this term a into e raised to I delta, that is amplitude together with the exponential representation of initial phase, that is amplitude with the phase term, phase constant term, is replaced with a complex amplitude. Complex amplitude is written like this: a is similar representation a with a. It is easier to know as AC signal symbol like this: a e raised to I kx minus omega t. Here look at this: a is equal to a e raised to I delta, which is the complex amplitude, and this term together with this I kx minus omega t, complex amplitude with this term is represented as complex wave function fxt. Okay, fxt. So this fxt is equal to real part of complex function wave function xt. So this is something, the complex notation. You can use any of this equation for solving problems. This is much easier to separate phase part or time part or the space part. That is the advantage of using this complex representation. So this is the representation, and we can say generally we can say a sinusoidal wave can be expressed as a linear combination of lots of sinusoidal waves, that is here minus infinity to infinity, that is the wave can extend to minus infinity, that is to the negative x direction up to infinity, and positive x direction up to infinity. That is why we are taking this integration limit as minus infinity to infinity. Then a e raised to I kx minus omega t plus dk. Okay, here omega and k are the omega is angular frequency and k is the wave number. Both are assumed to be positive here. Thank you.